we will going to learn about the shift and rotate instruction. So in this instruction here, okay, in shift and rotate, it is used to do a data shifting either to the left or to the right. Okay, there are few instructions available for data shifting and data rotation. Okay, one of them is we call it as a LSL. Okay, so LSL is stand for the logical shift left. Okay, so this logic, the actually, all right, the syntax for LSL is something like this, right? I will write the syntax here first. Okay, you have the LSL followed by your RD, destination register, and you have a RN, and after that, the number of, okay, how many times that you're going to rotate. Either you're going to shift to the, how many bit that you're going to shifting, okay, depending on the numbers here. Okay, for example, okay, you have the LSL, okay, then and the number of shifting that you're going to use is 4. Okay, so what happened here is, so now, okay, so this is what happened. Okay, since this is LSL, means that you're going to shift the bit to the left. How many times? 4 times. Okay, so we started, since we are going to shift to the left, so we started from the LSB. Okay, so this is your LSB, which is bit number 0, and you're going to shift it to the left 4 times, or okay, or 4 bits. So what happened here? Okay, started with bit 0. Okay, then you shift to the left 1, 2, 3, 4. Okay, 4 times. Okay, and then you copy this number here and it becomes here, right? And then what happens next is the rest of this bit here, okay, you will going to shift to the left as well 4 times. Okay, so all of this bit here, okay, you're going to shift to the left 4 times, and this is the final result that you will get. Okay, so this is for the LSL. Okay, then we have the LSR. Okay, LSR is stand for the logical shift right. Okay, so before that, I forget to mention. Okay, after you shift this bit here to the left, and what happened to remaining of this bit here? Okay, the remaining of this bit here, okay, you need to put it with a 0. Okay, so this is what happened every time you do the logical shift left. Okay, so the remaining of the bits here will, okay, will be filled by a 0 value. Okay, so this is, you fill it with a 0. Okay, for the LSR, logical shift right, okay, similar to the LSL, in which now you're going to shift your data to the right, depending how many time you're going to shift it. Okay, so since this is a shifting the data to the right, so we started with the MSB, which is a most significant bit, and you shift your data to the right depending on the number of how many times that you're going to shift it. Okay, for example, here you have you're going to shift it to the right how many times? 4 times. Then similar to what we did earlier, okay, from MSCB, bit 31, okay, you shift it to the right 4 times, okay, 1, 2, 3, 4, okay, and then you copy this value here to here, and the rest of the bits will be shifted, okay, this bit here will be shifted to the right 4 times as well. Okay, what about the remaining of this bit here? Okay, this bit here. What about this one? Okay, so this bit here will be filled by 0 as well. Okay, and then we have the ASR. Okay, so ASR stands for arithmetic shift right. Okay, so the arithmetic is quite similar to the LSR, but okay, the difference here is, okay, so you need to copy your most significant bit or your sign bits, okay, to fill up this value here. Okay, so this value here, okay, the value after you do the data shifting here will be determined by your sign number. Okay, either it's a 0 or 1. Okay, so let's look at this. Okay, you have a data, something like this, and then you're going to do the arithmetic shift right. How many times? 4 times again. So first, what you're going to do here is, okay, so this is your MSB or your sign bits. Okay, you copy this value here to here, right? First, we copy the most significant bit, okay, to bit 31 to our results, okay, and then we shift it to the right depending on how many times. Okay, since this is a 4 times, so if you shift to the right 4 times, and now it becomes 0 here, and the rest of this bit here, okay, this one here, okay, you copy back and put it here. Okay, next, what happened to this one? Okay, so this one here, the value of this one here will be filled by this sign bits. Okay, since the sign bit is zeros, then what you're going to do is you need to put 0. So your jawapan, your answer here will be in the positive value. All right, why? Because your sign bit is 0. Okay, and if, let's say, if you have a negative value, okay, a negative number, okay, so let's say this down here, okay, you have a value, this value here, okay, by using the same ASR, okay, so you're going to shift it to the right, how many times? 4 times. Okay, now first, okay, we locate our sign bit. So this is a sign bit, copy the sign bit, put it here, and then after that we shift to the right 4 times. Okay, so it become here, and the rest of the bits here you copy back and put it here, right? So this bit, okay, the rest of this bit you copy back and put it here, or you can shift it to the right 4 times. And what about this location here? In this location, okay, you will fill up with your sign bit. So that's why you see here 1 1 1. Okay, so this indicate a negative value. Okay, just to inform that every time you do the what we call here data shifting to the right, okay, actually you divide it by 2. Okay, if you do a data shifting to the right, to the left, actually you multiply by 2. Okay, if you shift it to the right 1 time, means that you multiply by 2. If you shift it to the, if you shift it to the left 1 times, okay, means that you multiply by 2. If you shift it to the left 2 times, means that you multiply by 2 multiply by 2, which is equal to multiply by 4. Okay, if 4 times, okay, so you multiply by 16 actually. Okay, 2 times 2 times 2 times 2, 2, 4, 8, 16. So, okay, so you will get multiply by 16 for data shifting 4 times. Okay, so the to the right means that, okay, every time you do the data shifting to the right means you divided by 2. If you to the left means that you multiply by 2. Okay, next. Now we look at this ROR. So another instruction is called ROR. ROR stands for rotate right. Okay, so this is a rotate right. So the difference from ROR and LSR is here is, okay, now, okay, you need to rotate all this data, okay, in one circle. Okay, for example, okay, you have this value here, right? And now you're going to rotate to the right how many times? 4 times. Okay, first, okay, identify your most significant bit. So this is your most significant bit. Okay, from here, you shift it to the right how many times? 4 times. Okay, and then you will come here. Okay, and next, okay, this remaining of this bit here, okay, will be go to this location. Okay, because this one here, if you rotate to the right, okay, what happened here is previously this value will go out. Okay, will go out from your register. But now what happened here? It will come to your register, become your most significant bit. Okay, so this is what happens every time you use the ROR. Means that your data will be rotate. Okay, you will do a data rotation in one circle. Okay, so means that there is no data sending out from your register. Okay, and what about the RRX? Okay, so RRX is another rotate, but with a extension. Okay, now we see here. Okay, what happened here is, for example, RRX1. Okay, means that you're going to rotate it how many times? One time, and the incoming. Okay, okay, the bit 31 here, the value will coming from your C flag, while the bit 0 here will go to your C flag. Okay, this is what happens every time you use the RRX. Okay, you need to consider the value from C flag become your bit 31, and the value from bit 0 will go to your C flag. And if you're going to rotate it a few times, okay, you need to consider this thing here. Okay, you need to consider this carry flags in your calculations. Okay, so this is for the data shifting and data rotation. Okay, so let's look at this exercise here. Okay, you are supposed to have this value for R0, R1, and R2, and the initial value of your NZ, C, and V is a 0, 0, 0, 0. Okay, so you need to find the value of the flags after each of the instruction. Assume that the instruction runs independently. Okay, so you have the first instruction, LSL R3 R0 #1. Okay, so what happened here? Okay, first, I'm going to ask you, okay, LSL, does your flags register affected for the LSL? Is this flag register will change according to this instruction here? No change. Why no change? Because you doesn't have suffix s after the LSL. Okay, so what happened is your N, Z, and C and V will remain 0. Okay, now we're going to look at this instruction here, LSL R3 R0 #1. So what happened here? So R3 is actually your RD, destination register. R0 is your RN, your source register. And 1, what is your 1? 1 is the number of operand, which is indicate how many times that you're going to rotate. Okay, since this one here, you're going to shift it to the left. All right, so value from R0, what is your R0? So this is your R0. Okay, so we have a F, 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 F. Okay, so I just take this byte and this byte only. Okay, the rest of the byte is similar lah. Okay, because the value is F, 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 F. Okay, so we have 1, 1, 1, 1, 1, 1, 1, 1. So this is bit 31. Okay, and then we have 1, 1, 1, 1, 1, 1, 1, 1, and this bit 0. Okay, so what are you going to do? LSL. What is LSL? Logical shift left. Okay, you're going to do a logical shift left. How many times? One time. Okay, since this is a to shift to the left. Okay, so we look at this LSB. Okay, bit 0. Okay, now you're going to shift this bit here. How many times? One time. So this is the value that you will get. Okay, so the rest all of the data will be shifted to the left by 1. Okay, what about this value here? Okay, this value will go outside. Okay, the bit from 31 will go outside. And what about the bit 0 here? Okay, the bit 0 here will be replaced by 0. Okay, 0 from outside will go replacing this bit 0. So this is what happened for the LSL. You see here? Okay, every time you do the LSL, okay, the bit here will be filled up by 0. And what about this bit here? This bit here will go outside of the registers. Okay, so what would be the result? Okay, the result will be R3 equal to F, 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 F. And what would be this one here? This is F. What about this one? 8 plus 4 plus 2, which is E. So this is your results. Okay, none of the flags changed or affected. Why? Because you doesn't have the suffixes S after your instructions. Okay, what about this one here? LSRS. Okay, what is LSRS? Logical shift right. Okay, R3, R1, how many times? Okay, once. Okay, so R1. So this is your R1. Okay, so I'm just focusing on this bit and this bit because in the middle here is the bit is similar. Okay, 1, 2, 3, 4. Okay, so this is bit 31. And have 0, 0, 0, 0, and 0, 0, 0, 1. Okay, now we're going to find out what is the flags here. Does the flags affected? Yes, it depending on, because since you have the suffixes s, so you need to do this first, and then after that you're going to find out what is your s value. Okay, so now, right? So now you're going to do the shift to the right. How many times? One time. Okay, since this is a shift to the right, so we're going to start with your MSB lah, bit 31. Okay, from here, you shift to the right. How many times? One time. So this one will become 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And this 0 here will fill up to here. What about this one here? This one will go outside. Okay. And what about this bit 31? Okay, the 0 from outside will fill up this bit. Okay, so what will be your R3 value? The R3 value now is 0, 0, 0, 0, 0, 0, 0, and 0. Okay, so now we're going to identify the flag register here. Okay, your N flags. Okay, what about your N flag? Your N flag will, okay, you're going to need to look at the bit 31. Since your bit 31 is 0, then the N flag is 0. What about your Z flag? Okay,
1.
Okay, your Z flag equal to 1. Why 1? Because the value here is 0. Your R3 is 0. What about your C flag? Okay, the C flag doesn't affect it. Okay, because in this LSR instruction, okay, there is no, okay, you're not affected any carry flag unless you use this RRX. RRX, yes, the carry flag will affect it. Okay, depending on the bit that it will go to this C flag here. So the C flag remains 0. What about your V will also 0. Okay, so and for the A and the S, so you can do the logical ANDs. Okay, and then see what are the flag that will be affected depending on this result of R3. Okay, this one you can do it by yourself. Okay, then we have another instruction, which is we call it as a to extend a sign bit. Okay, either you're going to extend a sign extension or 0 extension. Okay, we have a few instruction for bit extension. Okay, we call it as a SXTX. Okay, so this is for the sign extend, and UXTX, this is for the unsigned extend. Okay, so SXTX can be divided into two more. Okay, you will have a XXTB and SXTH. Okay, for the B stand for byte. Okay, which is you will going to convert a sign byte in your RN, okay, your source register, into a sign word by copying the sign bit, which is bit number 7 of your destination, of your source register into all the bit of your destination register. Okay, so B is for byte. One, if byte means that it's a 8-bit. Okay, meanwhile, for the XXTH, okay, it's similar to this one here, XXTB, but this one here is half word. Okay, means that it involves of 16 bit. Okay, for example, let's look at this one here. Okay, so you have R1. Okay, so this is the syntax XXTB R1 R0. Okay, you're going to extend the sign value from R0 and put it to R1. Okay, this is the value inside of R0. Okay, since this is a byte, okay, so what happened here is, okay, we are focusing on these bits only. Okay, so now we change this bit, okay, this hexa value to binary number. Okay, what is a D? A, B, C, D. D is a 13, yeah. Okay, so 8421, 8421. Okay, so 13 is, okay, so this is a D. Okay, so now, since this is a byte, okay, so we are focusing on this bit number 7. Okay, so what happened here is, first, okay, you copy the value back to here, okay, DD, and now we are looking at bit number 7. Since this bit number 7 is 1, so what happened here is, you will extend the bit here with 1, 1, 1, 1, 1, 1, 1, 1, 1, which is equivalent to FF, FF, FF. Okay, so this is the sign extend. Okay, another example. I give you another example. Okay, the value of R0 is, okay, we have this example, XXTB R1 with R3. Okay, let's your R3 equal to FFAB1, 2, 4, 3. Okay, so what happened here is, since this is a byte, okay, so we are focused on this bit only. So your R3, R1 will equal to, okay, we copy the 43. And this one here, okay, you change to binary, okay, and it will become, okay, 0, 1, 0, 0, 0, sorry, 0, 0, 1, 1. Okay, look at this sign, which is 0. Then the rest of the bit here, you will just put with 0. Okay, so this is the XXTB. Okay, what about that if you have the XXTH? Okay, sama lah. Okay, quite similar actually. Okay, now we are looking at this bit. Okay, because H is a half word, so you need to copy this 16-bit number. Okay, CC and DD, you copy back the value. And now look at what is the sign of this bit 16. Okay, since this is a CC, you know that, okay, your 8 will, your sign will be 1. Okay, so the value will be, okay, so this one here, okay, I just write down here. So R1 will equal to FF, FF, CC, and DD. Okay. Okay, next. Next is example is UXTH. Okay, what is UXTH? TH here. Okay, so this UXT, okay, you are going to extend your unsigned number, okay, in the RM and place in your RD. Okay, since this is unsigned, means that you doesn't need to look at this bit here. Okay, so it means you will always extend a 0 regarding of this value, even though this bit 7 here is 1, doesn't matter. Okay, you will extend the 0 because this is an unsigned numbers. Okay, for example here, UXTH R2 R1. So this is the value of your R1. Okay, so what happened here is, since this is a half word, okay, you copy this value here. Okay, copy the value. So you will get FFDD. Okay, even though this one here, you see FF, which is the bit number 60, is by right, you will have a 1. Okay, bit 16. But regardless of this bit here, okay, doesn't matter. Okay, since this is a U unsigned number, so you will extend the 0. Okay, so that's why you get 0000 FFDD. Okay, so this is how to do the signed and unsigned extension using these instructions. Okay, and then we have another instruction. We call it as a reverse instruction. Okay, so for the reverse instruction, we have 3 instructions available. First is a REV. Okay, so this REV will reverse the byte position of order of the 32-bit value in your source register, which is your RN, and place the result in the destination register, which is your RD. Okay, for the REV16, okay, this one here, you reverse the 16-bit position order of the 32-bit value in RN register and place the result in your RD. And last but not least, REVSH means that you're going to reverse the 16-bit position order of RN register. And after that, you extending the sign to the 32-bit in the RD. Okay, let's look at the example for more understanding. Okay, so suppose this is your R0. Okay, so this is the initial value of R0. And this instruction here is executed sequentially. Means that the second instruction will depend on the first instruction. Okay, so let's look at this example. REV R1 R0. So this is R0. Since you're going to do the REV, so what happened here is, okay, so REV will involve a 32-bit. Okay, so this bit here will go to this location. This bit will go to here, C here, and the least significant bit become your most significant byte here. Okay, so this is a REV. Okay, if you have the REV16, so what happened here? First, what you're going to do? Okay, since this is your R1, okay, the current value of R1, okay, you divided your R1 to half word. Okay, one is a lower half word and the other one is a upper half word or top half word. Okay, and then after that, you reverse the order, the byte order for each of the half word. Okay, so this A will go here, B will go here. And what about C? Similar, will go here, and this location here will go here. So this is the final results for REV16. And next, we have the REVSH. Okay, so means that you're going to reverse, okay, the lower half word, and then after that, the top half word will extend by the sign extension. All right. So first, okay, divided this value R2, okay, because this is instruction REVSH R3 R2. Okay, your source that register is from R2. Okay, so you divided it to 2 words. Okay, so this one is the lower half word and this is the upper half word. Okay, the lower half word is you reverse the order. Okay, so BB will go here, AA will go here. And what about the upper half word? Okay, you need to look at this bit here. This bit. Okay, the sign of this bit. Okay, AA. What is a AA? Okay, AA, if you change it to binary, you will get 1010. 1 0 1 0, and now you're going to look at this bit. So this is your bit 15. Okay, bit. Okay, so what happened here is you look at this bit and you see here the sign is 1. So that's why you extend the 1 after that. Okay, if the sign is 0 at this bit, so you will extend zeros at this half word. Okay, at the upper half word. Okay, any question up until here?
Clear, bro.
Okay, if no question, then we moving on to the next slide. Okay, so these are examples for the REV16 and REVSH. Okay, so let's look at these examples here. Okay, the first line LDR R1 OX1 2 3 4 5 6 7 8. So what happened here is, okay, you're going to put this value here, okay, to your R1. Okay, so R1 now we'll have this value 1 2 3 4 5 6 and 7 8. Okay, and then you change that REV R2 R1. So you're going to find out what is your R2 by using the reverse instruction. Okay, since this is involve the 32-bit, so what happened here is, okay, you identify lah. This is your most significant byte, and this is your least significant byte. Okay, so this byte here will go to this most significant byte, so they become 78. Okay, 56 will go here, 34 will go here, and 12 for most significant byte will become your least significant byte, 12. Okay, so this is the final results. Okay, next, we look at the second example. LDR R1OX559922FF. Okay, so what happened here is you're going to load this value to your R1. Okay, 559922 and FF. And after that, okay, please do a correction here. This is a REV. Okay, REV16. Okay, REV16 R2 R1. So you're going to find out what is your R2. Okay, since this is a 16, means that half word, okay, you divide it 2 and do the data reverse. Okay, so this FF will go here and this will go here, and okay, you swap the position, okay, and the value will be 9955 FF at 22. Okay, so this is for the REV 16. Okay, then we have the another example. Okay, LDR R1OX559922FF. Okay, again, R1 will have this value 559922FF. Okay, now REVSH. Okay, means that you're going to reverse the lower half word. You reverse the order of that byte, and after that, the top half word you will extend the sign value. Right? So divided by 2. Okay, so this is your R2. Okay, first, okay, swap the position. Okay, so it become FF22. Okay, what about this upper half word? Okay, so you need to look at this bit here. Okay, what is the sign value? Okay, 22, you change it to binary, you will get 00100010. So this is a 22. Okay, look at this bit. Okay, since the bit is 0, so what happen here is you will extend number 0. So that's why 0000. So this is your R2. Okay, and last but not least, okay, another reverse instruction called R bit. Okay, so this R bit means that you're going to reverse all the bit order in your 32-bit data. Okay, so this is what happened. Okay, you see here, the least significant bit become your most significant bit, and the rest of this bit here will be reversed accordingly. And your most significant bit will become your least significant bit, and the rest of this bit here will reverse. Okay, the order will be reversed accordingly. Okay, so this is what the R bit do. Okay, reverse the bit order in the 32-bit data. Okay, so that is for the reverse instruction. Any question, Amati, here? Okay, if no question, then we move on to the next instruction. Okay, which is we call it as a multiply. Okay, this is to multiply the between two registers. Okay, so this is the syntax or multiplication. MUL. Okay, sometimes you can follow with your suffix, and then you have a RD, RN, and RM. Okay, you have a destination register, source register, and the second source register. Okay, so let's look at this one here. This instruction MUL R2 R1 R0. Okay, so this one here, what happened here is R2 equal to R1 multiply with R0 because this is your source and this is the destination. What happened here? You multiply this register to register, put the result to R2. Okay, can I do this one? MUL R2 R1 hashtag 4 with the immediate value 4. Can you do that? Cannot. Why cannot? You see here, the syntax is between register. Okay, you cannot use the immediate number. So this instruction is invalid or illegal. Okay, cannot use a constant as your second source. Okay, what about this third instruction here? MUL R1 R1 R2. Okay, so this one is illegal. Why? Because the destination and the source is coming from the same registers. Okay, you cannot use the same source and destination register. Okay, this is only valid for the multiply. If you use the ADD subtract, you can use this source here as your destination as well. But for the multiply, cannot. Okay, so let's look at this example here. Okay, so first instruction, move R1 with 25. Okay, means that you're going to move this value 25 to your R1, move R2 with this value 65. So 65 will go to R2, MUL R3, R1, R2. So what happened here is R3 equal to R1 multiply with R2, and you will get a result. And this result here will be stored to your R3. Okay, what about the second one here? LDR R1 with this number. Okay, 100,000. LDR R2 with 150,000. Okay, and then MUL R3, R2, R1. Okay, so you can do the multiplication. Okay, but since if you multiply this number here, 100,000 multiply with 150,000, and then you see here, you will get a very large value, which is not fit to your 32-bit numbers. Okay, so what happened here is only the first 32-bit number will be stored to R3 while the remaining of the bits will be discarded. Okay, so make sure that, okay, if you're using the multiplication, make sure that you the number that you're going to multiply can fit to your 32-bit number, cannot more than that. If not, the value will be discarded.
So, Prof, what is the value of R3 here?
Huh?
What is the value of R3 here?
Okay, you need to multiply lah. Okay, first you multiply this number, this number, and then we get this value, change it to hexa, and then you find the value for the 4 byte of the hexa number. That is the value that will be stored to R3. The rest of the byte will be discarded.
Okay, thank you.
So, Doctor, the result will immediately store in R3.
Pardon?
When we multiply R1, R2,
Okay.
the result will immediately go to register R3.
Okay, let's see lah. Okay, I give us for example, okay, you have a R1 and multiply R2, and this is your, suppose this is the hexagon number that you will get. Okay, so for example, okay, so this is the value that you will get after you multiply R1 with R2. Okay, according to this value here, okay, you see this value here is more than 32-bit data. Okay, because this is the first byte, which is 8-bit. Okay, this is the second byte, third byte, fourth byte, fifth, and sixth. Okay, you have a 6-byte value. Okay, so what happened here is, okay, for the R3, okay, the value that will be stored to R3 only this byte. Okay, which is IB, IF, 3F, and 2F. IA and 22 will be discarded. Okay, this is what happened. Okay, if you multiply more than 16-bit data at one time. Okay, is it clear?
Yes, Prof. Much clear now.
All right.
Thank you so much.
Okay, so that's why for the multiplication. Okay, so just to remind you, okay, for the multiplication, okay, make sure that your source register, okay, your RD and RM is smaller, okay, is less than 60-bit number. Okay, because 16-bit multiply with 16-bit, okay, you will get 32-bit numbers. Okay, so make sure that the value is smaller than 60, is a 16-bit number, cannot more than that. Right? If you have a 17-bit number, then you need to discard the excessive value, okay, excessive result from the multiplications. Okay, moving on to the next slide. Okay, now we're going to look at the load and store instruction. Okay, we have a lot of load and store instruction that you need to know. Okay, so this is okay, before we look at the load and store instruction, okay, let's look at the transfer size. Okay, what are the size that you can transfer at one time? Okay, either you're going to load a data or you're going to store data. Okay, we can transfer a word of data, which is a 32-bit numbers at one time. Okay, you can transfer a half word, which is a 16-bit data at one time, or you can transfer a byte of data, which is 8-bit data at one time. All right. So, and multi-word, okay, so this is by using the LDM and STM. Okay, we are going to focusing on these three only. Okay, word, half word, and byte data type. Right? For word, okay, the instruction that you're going to use is LDR. Okay, every time you look at the, you come across with LDR, you know that you're going to transload a 32-bit number. Okay, so LDR can be unsigned number and signed number. So both signed and unsigned number will be used the same LDR instruction. Meanwhile, to store a 32-bit number, okay, we will use the STR. Okay, this is for the 32-bit data. Okay, if you're going to load a 16-bit number, okay, so we are going to use the LDRH for unsigned load and LDRSH for signed load. Okay, so this is for the 16-bit number. What about to store? Okay, to store, you're going to use the STRH. Okay, every time you look at this H here, okay, you know that you're going to load or store that 16-bit numbers. Okay, and meanwhile for byte, which is 8-bit, okay, the instruction to load a 8-bit number is LDRB. This is for unsigned, and for the signed, you can use the LDRSB. Okay, store is STRB. So every time you look at this at the end of the instruction with the B, means that you're going to move a data with a 8-bit size. Okay, so basic load and store use a register indirect addressing mode. Okay, previously we already learned about indirect addressing mode. What is an indirect addressing mode? Means that, okay, if you can see here, okay, LDR R0 R1. Okay, since R1 here, you see you have a bracket, means that it is an indirect addressing mode. Okay, what happened here is you need to go to your R1, check the value inside your R1, and then after that, you go to the memory address pointed by your R1, take the value and put it to your R0. So this is the indirect addressing mode. Okay. So for the LDRH, okay, what happened here is, if you can see here, okay, since this is involve the half word 16-bit numbers, okay, 16-bit data. So what happened here is, okay, you will go to the location, okay, that are pointed by R1 and take only this half word, okay, the lower half word, which is from bit 0 to 15, and put it to your R0. So this is what happened. And meanwhile, for the LDRB R0 R1, okay, what happened here is you go to the location pointed by R1, take the value, but you only take a byte of data, okay, which is 8-bit data from bit 0 to bit 7, put it to your R0. Okay, so this is what happened. Okay, so this is for the LDRH. Okay, you just take the 16-bit numbers from the destination registers, and the remaining of this 60-bit will be filled up with 0. Okay, for the loading a byte using LDRB, so you just take a 8-bit number, okay, from your registers, okay, your destination, your source register, and remaining of this 24-bit will be filled up with zeros. Okay, later we will see more details on this part here. Okay, so this is the penerangan, or the, okay, it's telling you how the indirect addressing mode works. Okay, so first, okay, so you will do the LDR R0 R1. So this is your, okay, so this is your address, okay, memory address. Okay, so this is your EEPROM, and this is your RAM, and this value here is your memory address. So since every time our instruction will be stored inside the EEPROM and program code, okay, so what happened here is the program counter will go to these addresses here, takes the instruction here, and this instruction will be decoded. Then after that, the CPU know what you're going to do. Okay, so this one is in LDR R0 R1. So what happened here is you go to the R1. Okay, so R1, this is your R1, and this R1 here value is to this value. All right, so this is the value inside of R1. So what happened here is, okay, it's telling you to go to this address inside of your RAM, and what happened, the CPU will go to this address here inside of your RAM, take the value and put it to the R0. So this is how the indirect addressing mode works. Okay, so let's look at these examples. Okay, so we have the LDR R7 R5, and then what happened? Okay, assume that R5, okay, it's telling you that R5 equal to, so this is the value of R5. Now what you're going to do here is LDR R7 R5. Okay, so this is the value inside R5. Okay, so what happened here is you go to the address pointed by R5, which is at this address here. Okay, so this address here is actually inside of your RAM. Okay, go to this location. So this is the location. And now what happened here is, since this is LDR, LDR means that you're going to load a 32-bit numbers. Okay, and since, okay, remember, okay, the data memory size is always 8-bit. Okay, so that's why, since this instruction here involve a 32-bit, that's why you need to have a 4-byte here. You need to load a 4-byte from this address, started from address, this address. Okay, I just call it as a 200, 201, 202, and 203. Okay, to make up a 32-bit data. Okay, if you take only from 200, means that it's only 8-bit data, which is wrong. Okay, since this instruction here telling you to take a 32-bit, to load a 32-bit number started from address 200. So you will go to this address. Okay, so this is the first 8-bit data. This is the second 8-bit data, third and fourth. Okay, so now what happened here is, okay, so this is the value. Then this value, this 32-bit data, you're going to put it to your R7. Okay, so this is what happened. Since this is we using the Little Indian. Okay, so we put this one to here, LSB. Right, this value to here, and C5 to here. Okay, so this is what happened. Okay, go to address pointed by R5. Okay, so this is the address pointed by R5. Since inside here only have a 8-bit data, so you need to get a 32-bit data. So you need to, okay, go to this address 201, 203, 2 and 203 to make up a 32-bit data. Okay, so this is for the LDR. Okay, moving on to the LDRB. Okay, again, R5 point to this address. And then you have LDRB, R7, R5. Okay, so first thing first, what happened here is, okay, we're looking at this. Okay, this instruction asks you to take a byte of data from this location pointed by R5. Okay, so you go to this location. Take a byte of data means that only copy 8-bit data. Okay, so this is enough. Put it to your R7. So that's why your R7 will have a 74. What about the remainings of this bit here? Okay, the remaining of this bit will be filled up with 0, 0, 0. Okay, even though, okay, inside of this 201, 202, or 203, you have a different others value. Okay, so this value will be ignored. Why? Because you only, okay, want to load a 8-bit data, not 32-bit data. So that's why only 8-bit data will go here, and the remaining of the bit will fill up with 0. So this is what the LDRB do. Okay, which is the instruction tell the CPU to load or copy 1 byte from an address pointed to by your R5, okay, into the lower byte of R7. Okay, next, LDRH. Okay, again, we have the, assume that the R5 value is this value, inside of R5 have this value. Sorry. Okay, 0200. and LDRH R7 R5. Okay, so what happened here? Okay, look at this one. Half means that 60 bit. Okay, you're going to load a 60 bit number from location pointed by R5. Okay, you go to this location. Okay, 4200 and take only 16-bit number. Okay, so 16-bit number is this number here. Okay, put it to your R7. Okay, what about 41 and 52? Okay, just discard this value. Okay, no need to look at this value. Only the lower 60-bit number will be loaded to your R7. So that's why it's 74, 63. What about this bit here? Okay, the remaining of the bit will be filled up by 0. Okay, so this is what happened. Okay, the LDRH will tell the CPU to load or to copy a half word or 16-bit number from a base address pointed by your R5 and put it to your R7. Okay, that is for the what we call load. Okay, then we'll moving on to the next. This slide here, this is for the store. Okay, similar to load. Okay, for the store, you can also store a 32-bit data by using the str or 16-bit data by using the strh and 8-bit data only by using the strb. Okay, so the way it works is similar to the LDR instruction. Okay, let's look at the examples. Okay, so assume that, okay, so this is your R6. R6, okay, will have this value, okay, 4200. Okay, now you're going to, and R3, okay, it's telling you that the R3 value is this value, 4152637 Okay, you're going to store R3 to the location pointed by R6. Okay, so since this is a 32-bit, okay, STR is a 32-bit, so what happens is you go to this location pointed by R6. Okay, so this is the location. And now, store the value from R3. Okay, since this is your R3, okay, so this is your R3 data. Okay, so this is the 32-bit or R3 data. So what happens here is, okay, so this data story will depend on either you using the Little Endian or Big Endian lah. So in this case, we are using the Little Endian. So that's why SETv24 will be stored at address 200. 63 will be stored to the next address, which is 201, 52, this address 202, and 41 to this address 203. Okay, so 32-bit data is stored at the base location started from this address 4200. Okay, so what happened here is the STR instruction will tell the CPU to store the content of the GPR, all the content of 32-bit of the GPR to a base address location pointed by your destination registers. Okay, sorry. Too fast. Okay, next we have the STRB. Okay, let's look at the STRB. So what does STRB do? Okay, assume that R5, okay, value is, okay, the same address, okay, 4200. And then your R1, 41526374. And this is the instruction that you're going to do, STRB R1 R5. Okay, so what happened here? So now you're going to store a byte, okay, 1 byte data, right? So this one here, So 8-bit, only 8-bit you're going to store from R1 to R5. Okay, so first, what you're going to do is you go to R5. Okay, so locate your address pointed by R5. So this is the address pointed by R5. And now, okay, since this is your R1, okay, so, okay, do you divided your R1 to 4 byte? Okay, 74, 63, 52, 41. Okay, you divided them to 4 byte and takes this value, since this is a byte, takes the least significant byte and put it to this address. Okay, only 8-bit data will be stored to this address. What about 41, 52, and 63? Okay, so this one here, you just ignore. You just going to store this byte only, okay, the 74 only to your this address. Okay, so this is for the strb. Okay, and if you have the strh, okay, so again, okay, so R6, okay, this is R6, okay, R6 is telling that assume that R6 is 2000. Easy to, okay, very easy, all right, 2000, okay, easy to name this value here, okay, because the value is very small. And the R3 is a 32-bit number with 41, 52, 63, and 74. Okay, then you have the STRH, R3, and R6. Okay, so what happened here? You're going to store half word, okay, from R3 and put it to the location pointed by R6. Okay, so now we go to address pointed by R6, which is at address 2000. Okay, so go to this location and store the half word. Okay, so this is your R3. You divided your R3 to 2 half word. Okay, so this is the lower half and this is the upper half. Okay, so now what happened is you just copy the lower half, which is a 60-bit number, okay, to your address pointed by R6. So 74 will store to address 2000, while 63 will store to address 2001. What about 41 and 52? Okay, 41 and 52 inside of your half word, upper half word will be ignore. Okay, so this instruction STRH will tell the CPU to store the lower 16-bit content of the destination register, of the source register to an address location pointed by your RD register. Okay, next, moving on to the next slide. Okay, we have the sign load instruction. Okay, so what this sign load instruction do? Okay, the sign byte and half word are loaded from the memory with sign extension. Means that similar to what we did earlier. Now, the remaining of the bit will be filled up by your sign number. Either it's a 0 or 1 depending on your sign bit, right? So this is if you're going to load a half word, you did the LDRSH. Okay, so you just load 60-bit number to this register, and the remaining of the bit will be filled up by the sign bits. Okay, what about the LDRSB? Similar. Okay, you just load the 8-bit to your register, and the remaining of this bit here will be filled up by your sign bits. Okay, depending on the sign value, either is a 0 or 1. And then another instruction for the LDR, okay, to load by using the indexing methods. Okay, so we have a 4 addressing mode of indexing. One is an immediate addressing mode with a 0 offset, okay, without any offset. So this is instruction LDR RN means that the effective address of RN is RN lah, because you doesn't have any offset here. Okay, you just go to the address pointed by RN. Okay, take the value, put it to your destination register. And then we have the immediate addressing, okay, with an offset. Okay, so this is the instruction LDR RDRN, comma, hashtag K. Okay, so what happened here is you have an offset. So what you're going to do, you need to add your RN plus your K, and then that will be your effective address. Okay, so what happened here, after you get the effective address, go to the address, take the value, put it to your RD. Okay, then we have a register addressing. Okay, similar to the immediate addressing with offset. So what happened here is now your K, okay, is changed with your RM. So what happened here is you need to find the effective address. The effective address is RN. Okay, the address pointed by RN plus with the address pointed by RN. Get the effective address, go to the address and load it to your RD. And last but not least is a scale addressing. Okay, so the scale addressing is LDR, RD, RN, RM, LSL, hashtag N. Okay, so what happened here is you need to do a data shifting first for your RM. Okay, do a data shifting. Either it's a shifting to the right or shifting to the left, depending on this operation here. Okay, once you get the data shifting from RM, then you plus with your RN. Then after that, you will get the effective address. Once you get the effective address, go to the address and load it to your RD. Okay, just take note that the immediate value is a 5-bit sign number. Okay, so this immediate value only 5-bit number, cannot more than that. If more than 5 bits, what happen is, okay, there will be an error. Okay, the instruction will have a syntax error. Okay, so let's look at how to do the load and store with a base and offset. Okay, by using the offset here. Okay, for example, here you have a LDRB, R0, R5, and 3. Okay, hashtag 3. Okay, so let your R5 point to this address. Okay, 2 million. Is it 2 million? No, it is not 2 million. Okay, 20 million. Okay, so what happened here is, okay, before you go to this address, okay, you need to find out the offset dahulu, the effective address, which is you need to add with the offset. So you plus with 3, and then the effective address is actually at this address. Okay, so what happened here? Okay, so this is a base address plus with offset, and this is the effective address. Go to this address, take the value and put it to R0. Okay, so this offsetting or indexing method also applies to the store str instruction. Okay, so now we moving on to the next slide. Okay, this is a indexing addressing. Okay, there are 2 types of index addressing. Okay, one is we call it as a pre-index. Okay, means that you need to include the offset first in to become your effective address, or post-index. Okay, what happened for the post-index? You take the base address, then after that load to the location, and after that you store the offset. Okay, so let's look at this pre-index and post-index. Okay, for the pre-index, there are 2 types of pre-index. One pre-index without a write back, and the second one pre-index with a write back. Okay, so this is the syntax without a write back, which is LDR, RDRN, hashtag K. Okay, so this is the effective address. Okay, so effective address is actually this value plus with this value. Okay, you will get the effective address. what about your Rn? Does your Rn change after that? No. Since this is not with a right bet, your Rn remains. Okay, similar to this one here. Does your R5 change after that? No, your R5 still have this value. Okay, 20 million. Okay, doesn't change. Okay, if you do a pre-index with a right back, okay, LDR, RD, RN, hashtag K, and then you have this symbol here, exclamation mark symbols. Okay, so what happened here is, first you get the effective address by add these two numbers here. Okay, these two numbers, you add them together. And this, you go to that address, take the value and put it to your RD. And what about your RN? Okay, your RN will change, okay, after the education. So now your RN change to this value. Okay, for example, okay, I use the similar example here. Okay, so this one here, I just use the LDRB R0 R5 hashtag 3. And then with this symbol here. So what happened here is, after I execute this line, my R5 now become this value. Okay, we'll have the new value. But for this one, the R5, the value is remain, no change to the value of R5. Still 20 million. But this one here is 20. Okay, 20 million with N3. Okay, so that is for the pre-index with a right bet. And what about the post-index? Okay, for the post-index, okay, so this is the syntax LDR, RD, RN, hashtag K. Okay, since the hashtag K is outside of this bracket here, so what happened here is, first you get the effective address. Okay, the effective address is this, the address pointed by this register. Go to that location, load the value, put it to RD. Then after that, the RN, okay, will change with your offset value here. Okay, that's what we call it as a post index. Means that first you take the base value, go to the location. After you execute that lines, then after that your source register, the value will change with the offset value. Okay, so let's look at this example for the pre-index and post-index. Okay, suppose you have the str r0 r1 hashtag 12 and your r1, okay, have this value 200. Okay, so what happened here is, for the pre-index, okay, since this is in, okay, the offset is inside of this bracket here. So what happened here is, you need to find the effective address. So the effective address equal to 200 plus with 12. Okay, bear in mind that this 12 here is decimal number. Okay, so you need to change it to hexadecimal. 12 in hexa is C, A, B, C. Okay, so that's why the effective address is 200 C. Okay, so what happened here? Okay, so you go to this base address plus with offset. Okay, so the offset now is 200 C. Take the value and put to the, store the value from R0 to this location. So your R0 supposed to have this value 5. Okay, so what happened? You store this value 5, put it to address 200C. Okay, what about your R1? Does your R1 change? No, your R1 remains 200. Okay, why? Because you doesn't have this symbol at the back of your instruction. And if you have this symbol after this instruction, what happens is your R1 will change to 200C. Okay, with this instruction symbol, then your R1 will have this value. Okay, for the post index, suppose you have the str r0 r1 12. Okay, so again, okay, R1 is 200. Okay, so R1 is pointed 200 and the value of R0 is 5. Okay, you're going to store this value here. So what happened here is, since this bracket, okay, this 12 here is outside of the bracket. So what happened here is, okay, you go to this address 200. Okay, store the value from R0 to this location, 200. And then your R1, okay, will have new value, which is you need to offset with 3. So your R1 now will point to this address 200C. Okay, that is for the post index. So this is another examples of the register indirects. Okay, we have a plenty of value here. Okay, so let's look at line by line what happened here. Okay, we're not looking at all of these instructions. We only look at some of the instructions. Okay, first LDR R0 R1 hashtag 4. So what happened here is, first you need to find out the effective address. Okay, the effective address here is R1 plus 4, and go to the location, put the value to your R0. Does your R1 change? No, your R1 remains. Okay, what about this one here? LDR R0 R1 hashtag 4, and then you have this symbol here. Okay, again, find out the effective address. The effective address is R1 plus 4, and then go to the location, load the value, put it to R0. What about your R1? Your R1 will change, which is your R1 now equal to R1 plus with 4. Okay, you see here? Okay, so this is the value of your R1. Okay, what about this one here? LDR R0 R1 and then comma hashtag 4. So this is a post index. Means that you need to go to a location pointed by R1, take the value, put it to R0, and after that, your R1 change with this offset here. So R1 equal to R1 plus 4. This is a post index. Okay, let's look at this one here. Okay, LDR R0 R1 LSL 2. Okay, so what happened here? Okay, so now what happened is, okay, you need to go to the address location pointed by R1 after you do this LSL. Okay, you do the rotation to the left 2 times, go to that location, get the value and put it to your R0. So that is what happened. Does your R1 change? No, your R1 will remain. Okay, the rest of the example you can look it by yourself. Okay, the explanation you can find it under this comment section. Okay, so whenever assembly operand are included in a square brackets, okay, this implies memory is getting access, and this requires load or store operation. Okay, so every time you look at this bracket here, the square bracket, you know that that is belong to a memory address. Okay, you need to go to that memory address pointed by your registers. Okay, so this is what the meaning behind of this brackets. Okay, it indicates the indirect addressing mode, means that you need to go take the value, go to the value pointed by your registers. Okay, that value is inside of your memory address. Okay, you can use the PC, the program counter, as your base address. Okay, so this is what we call it as a PC relative addressing. So contoh LDR R0 PC and offset. Okay, so you will go to your PC. What is your PC value? Take the value and add with your offset. Or sometimes you can use the stack pointer as well as a base address. So this is the instruction LDR R0 SP hashtag offset. Okay, so this is similar. Okay, take the value of your current stack pointer, add with your offset, go to the location, take it and put it to your R0. And for the MOV, okay, MOV you cannot use this bracket here. It is illegal. Why? The MOV is for register between register and register between immediate value. Cannot register with memory address. It is illegal, so you cannot do these things. Okay, so this is a pseudo instruction. Okay, why we use a pseudo instruction? Because sometimes, every time, because if you're going to load data that is bigger than 8-bit, you cannot use the MOV instructions. Okay, the MOV instruction just for the 8-bit data. So in order to overcome that, you can use the pseudo instruction, which is by using the LDR and then followed by your destination register and equal to your immediate value. So the immediate value can be up to 32 B. Okay, so this is what we call as a pseudo instruction in order to load 32-bit data to your registers. Okay, and for the LDR, you can also load the data from the specific address into a register. Okay, if the address is okay, for example here, LDR RD label is your addresses pointed. The address is pointed by the label, so you go to the address pointed by label, take the value and RT. So you can use this instruction as well for the LDR instruction. Okay, to load a data from a specific address into a register. So this is another example. We have examples here. Okay, so this is a pseudocode. Okay, LDR R0 equal to OX 1, 2, 3, 4, 5, 6, 7, 8. So what happened here is, okay, you're going to put this value to your R0. Right, so this is a 32-bit number to R0. And if you use LDR R1 equal to 10, means that you're going to put a decimal value 10 to R1. Okay, by right, your R1 will have this value, not 10, yeah? It will have, because your register always in hexadecimal, your R1 will have this value 0A. Okay, so this is indicate a number 10. Okay, if you put something like this, LDR R2 equal to, and then you have this symbol here with A, means that you're going to load A to your R2, a character A to your R2. Of course, you not simply put your R2 will not have this value. We will not have A. Okay, the A here is indicate your the what we call it, the ASCII value. Okay, the ASCII value for the character A. So that the ASCII value of a character A will be stored to your R2. Okay, so this one here, if you're using the label, okay. So what happened here? LDR R0 numbers. So what happened here? You're going to load a numbers, a labels here, numbers, which is this number here you see here. Okay, you already define the number is a 25. So 25 will be loaded to R0. Okay, so this is an example how to use the LDR instruction. Okay, and this is an example of the programs. Okay, so this is a flow chart. Okay, we started with load first number, load a second number, add first number and second number, divided by 2, store the result. So this is, okay, what happened here is you're going to load two numbers. Okay, you're going to add two numbers and divide it by 2 and store the result. Means that you're going to find the average of two numbers. Okay, so how to do the programs? Okay, okay, so you started with this header here. Okay, so ADR R1 first num. Okay, means that you're going to ADR. What is the ADR? ADR is add, okay, the address from first num to your R1. Okay, load the number from this address to your R1 by using the ADR instruction. Okay, so this one here, R1 will have the first num, R2 will have the second num, then address tree will have the average results. Okay, and then LDR R4 R1 means that you're going to load the value pointed by R1, which is the first num, to your R4. LDR R5 R2, okay, get the second value, which is at the second num, okay, put it to R5, add this value here, ADD R0, R5, and R4 and R5. So add this value. After that, you put it to R0, and you're going to divide it by 2. Okay, to divide it by 2, you can use this ASR here. Okay, remember that every time you shift to the right means that you're going to divide by 2. Every time you shift to the left means that you multiply by 2. Since this is a divided by 2, so you just use the hashtag 1. Okay, only one times. Okay, get the results, store it. Where you're going to store it? You're going to store at this location here. Average result. So this is the instructions. Okay, so this is a program how to add two numbers and put the result to this address, average result. Okay, any question up until here? Okay, we have finished about the load and store instructions, data movement, and then we have the arithmetics, logical, data shifting, and bit rotation. Any question up until here? Okay, so in the quarter M4, okay, there are two branch instructions, okay, that you need to know. Okay, one is we call it as an unconditional branch. And the second one is a conditional branch. Okay, what is an unconditional branch? What is a conditional branch? Okay, so unconditional branch is a branch or a jump. Okay, you can jump or branch anywhere without the need to meet a certain condition. Okay, means that, okay, no need to look at a condition. No condition. Okay, you will jump here and there without any condition. But for the conditional branch, okay, the branch only happen if a certain condition are met. Okay, so if the condition met, then after that you branch or you jump to that addresses. Okay, so this is a example of the branch instruction available in ARM assembly language. Okay, we have the B. B is stand for branch unconditionally. Okay, means that no need to meet a certain condition. You just branch it anywhere, anytime you like. Okay, so by using this B. Okay, for example, B label mean that you ask the PC go to this label. No need to look at the condition. Okay, and then we have the BCC. Okay, so CC here you can put a suffix after that. Okay, we already learned about the few suffixes available, which is such as not equal, equal for EQ, high, low, etc. Later on, we will see more details on this part here. Okay, the BCC is stand for branch on condition CC. Means that you need to meet the conditions. After the condition is met, then after that, the PC will jump to that location. Okay, so this is an example. BCC with a label. Okay, the PC equal to label. Okay, the PC will go to this location address name label if the CC is met. Okay, and then we have the BL. Okay, branch and link. Okay, so this is always used when you going to do a subroutine. Okay, so why? Because we use the LR, the link register for this one. Okay, BX. Okay, branch and exchange. Okay, this one here is also used in the subroutine. Okay, so if you're going to return from a function or subroutine, okay, you can use the BX. Okay, and BLS as well as used in the subroutine. So this one here, this three is used for function of subroutine. Okay, and let's look at this more details on the branch with a condition and a branch without a condition. Okay, so this is BCon. Okay, stand for branch. Okay, and then so this B with a condition, the branch will happen if the condition is met. Okay, so for example, okay, currently you doing a function 0, and then at the middle here you have a B function 1. Okay, so it will go to this function 1, but after you finish the function 1, it will never back to this function 0. So this is what happened to the branch. Okay, for the branch with a link, okay, or BL, so what happened here is you currently do the function 0. Okay, in the middle of function 0, you call a BL function 1. Okay, means that you're going to do a function 1. Okay, it will go to this function 1, finish this function 1, and it will return back to this function 0. So that is the difference between the branch and branch with a link. Okay, for the branch, once the branch is finished, it will never goes back to where it stop. But for the branch with a link, one the function one is branch and the branch is finished. Okay, the function is finished, then it will go back where it stopped earlier. Okay, so this is the branch examples. B target, okay, means that you're going to ask the program counter to go to this location called a target, okay, without any condition met. Okay, so since this is without a link, means that once you go to this target, and you will never return back to the previous location. Okay, so this is another branch, MOV R15R0. Okay, which is this branch here asks the program counter, okay, to take the value from R0, okay, to and put it to R50. Okay, and this is another branch. Okay, LDR R15R0 means that this one here, it asks the CPU to go to the address in memory specified by R0, and the memory will go to that location and take the value and put it to R50. So we have a multiple branch example actually. Okay, so the most common one is by using the B instruction, but this is an uncommon one. Okay, we use it but never realize that this is belong to branch instruction. Okay, so there are two types of branchings. Okay, one is we call it as a branching forward, and the second one is a branching backward. Okay, what is a branching forward and what is branching backward? Okay, for the branching forward, what happened here is you will skip some of the code after this instruction. Okay, so this is what we call as a branching forward. Means that some of the instruction after this instruction branch will be ignored or will be skipped. Okay, why? Because you put something like this, BFWD. So what happened here? It will go to this instruction, to this location, and never do the instruction after this after this BFWD instruction, right? It will directly skip all the instruction after this. Okay, what? Meanwhile, for the branching backwards, so what happened here is means that you're going to creating a loop. Okay, every time we creating a loop, we using the branching backward. Okay, so this is you run instruction, and then if suddenly if you look at a B back, okay, where is the location of the back? Okay, it's top here. So it will go back here, do again, and it will keep repeating and repeating until the condition is false. Okay, and just bear in mind that a conditional branch are more useful than unconditional branch. Okay, why? Because the conditional branch only happens once the condition is true or once the condition is met. But for the unconditional branch, every time you ask the program to jump here and there, it will automatically jump here and there without checking any condition. Okay, and the comparison operation combined with a conditional branch allow the computer to act on a decision. Okay, so every time you're going to use a conditional branch, so make sure that you need to do some comparison. And this comparison here is needed in order to check the flags. Why? Because every time you do the branch with a condition, okay, the instruction will check the flags accordingly. Either the flag is true or not according to the branch conditions. Okay, so this is how you're going to setting a flag. Okay, in order to setting a flag, okay, you can use this instruction here. Okay, one we call it as a CMP. Okay, which is you're going to compare, and CMN is a compare with a not instruction. TST is a test. Meanwhile, the TEQ, okay, so this is another test. All right, and sometimes you can put the S, okay, here, suffix every time you do the data processing, and the flag will update accordingly. Okay, for the CMP, okay, contoh lah, okay, if you're going to compare R1 and R2, so what happen here, the flag will be affected, okay, accordingly, but the destination will not modify. Okay, you see here, CMP R1, R2, so what happen here is, you're going to, the CPU will subtract R1 with R2, okay, and the value of the flags here will be updated accordingly. What about the R1? Is the R1 change? No, the R1 will not change after that. Okay, because you just do a comparison. Similar to this one here, CMN. Okay, so this is a compare but with a not instruction. Okay, what happened here is, you see R1 plus with R2. Okay, this is the description. You add these two numbers here, and the flag will be affected accordingly. And what about your destination? Is it a destination modify? No, the RY value will not modify. Okay, the RY value will remain. Okay, similar to TST and TQ. TST and TQ will looking at the Z flags, and the value of R1 and R2 will not affected. What about the ADDS and sub S? Okay, this one here. Okay, so the flag will be affected, of course, yes. Why? Because you have the suffix S after that, and the destination register also affected. Okay, so that is the difference between the CMP, CMN with the ADDS and SUBS. Okay, so let's look at more details on this CMP, CMN, TST, and TEQ, what they do. Okay, so the CMP, okay, R1 and R2, okay, means that you're going to compare R1 and R2 by using the operation of R1 minus of R2. And this flag here will update accordingly. Okay, so if the MSB of R1 minus R2 is 1, so means that you know that R2 is bigger than R1 because this is smaller minus with R2, and then suddenly your MSB of your MSB from this subtraction is equal to 1. So you know that you produce a negative number. Okay, means that R2 bigger than R1. Okay, for example, if R1 minus R2 equal to 0 and Z suddenly equal to 1, means that you know that both number are equal. R1 equal R2 because R1 minus R2 and the result produce 0. So that's why Z equal to 0. If carries are equal to 1, okay, so this is, you know that both R1 and R2 are unsigned integers. So you know R1 is smaller than R2. And this is for if these are equal to 1. Okay, so this is again, R1 smaller than R2. Okay, and then this is for the CMN. Okay, set the condition code according to the result of R1 and R2. These flags here will update accordingly. Okay, TST also. Okay, set the Z flag condition according to the result of R1 and R2. Okay, you do a logical AND and then check the Z flags. Okay, so this is used to determine if one or bit are set, and while for the TEQ, set the Z flag according to the result of R1 exclusive or R2. Okay, so this one here used to determine if two operands are same or different. Okay, and this is the code suffixes that you can use for the branch. Okay, for the conditional branch. Okay, we have the EQ for equal. Okay, the flag that need to check is a Z flag. If Z equal to 1, okay, you know that both number are equal. Okay, for NA not equal. Okay, so the flag that you need to check is Z equal to 0. Okay, so you know that every time you subtract two number and the number and it produce a value, so you know both number are not equal. Okay, if you're going to check higher or same for the unsigned number, okay, you can use the CH or HS, and lower and unsigned by using the CC or LO. If you use a suffix mi, okay, so this is for the negative. Okay, so if you're going to check a negative number, so the flag that will need to be checked is an n equal to 1, so you know that the value is a negative number. And PL is for positive or 0. Every time n equal to 0, so you know that you have a positive number. Okay, for overflow and non-overflow, you can use the suffix VS and VC. And if V equal to 1, you know that overflow occurs, and VC equal to 0 and V equal to 0, so you know that overflow, there is no overflow. Okay, and this is another comparison for high and low, but this is a higher and lower or same. Okay, this is for the unsigned number. And if you have a signed number, you can use the GENLT instruction. Okay, GELT, GTLE. Okay, so this instruction here is used for unsigned. Sorry, for the signed number, for the comparison to check whether this number is lower or greater. Okay, and then we have this is how to use the conditional branch. Okay, for examples. Okay, so these are examples here. Okay, first by using a CMP. Okay, to check the flags. Okay, so this is example, right? So you compare your R0 with number 0, check whether your R0 is equal to 0. If your R0 is not equal to 0, so what happens here, you will keep looping and looping. Okay, so this is by using the CMP to check a flag before you do the branch condition. And instead of using a compare, you can also use the suffix s, okay, to check the flag whether the condition is met or not. Okay, so this is by plus the suffix s in the instruction, so you know you can check whether okay the value is 0 or not. Okay, so this instruction here actually similar lah. Okay, this both instruction is similar, one by using a compare and this one by using the sub. Only that, okay, this one here you save one instruction, this one here you have a one extra instruction, which is a compare instruction. Okay, and then we have a few instructions. Okay, so the one that you always use is an MRS, MSR. So this one here, this is how you're going to access the status register of special registers. Okay, so MRS means that move data from status register to a register, and MSR move data from register to a status register. So this is always used inside of the special register by using MRS and MSR. We already used this instruction several times in the special register that you already learned earlier. And then we have the CPS. Okay, so this CPS used to change a processor state Okay, so you can use the CPSIE and CPSID to enable or disable a certain interrupt. Okay, I is the bit lah that you're going to, or the priority, the interrupt priority that you're going to enable or disable. Okay, then we have the DMB, DSB, ISB. So I just keep this part. Supervisor SVCs. Okay, if you're going to use a low power mode instruction, so this is a instruction that enable WFI, wait for interrupt, WFE, wait for an event, SEV, send event. So this is by using the low power mode in order to save your power consumption and put your processor to sleep. And this is always used. NOP, no operation, means that you're just going to what we call here, to waste some time. Okay, you can put an NOP. BKPT is for the breakpoints, and this is some of the instructions commonly found on the processor and are implemented differently on the cortex. Okay, for not, okay, if you learn about the AVR instruction, okay, you have the NOT, but in cortex we use the MVN. Okay, if you use the NEG for the second complement, in cortex we apply the RSB, okay, etc. Okay, so that is for the instructions set for ARM assembly language. Any question up until here?